Hello and welcome to part 4 of Dev Maths and Stats Refresher Course, Lecture 5. Now we're going to look at total differentials. So, when you find a differential, but you take into account all the variables in the function, that's called a total differential. And in the two cases above, the formulas that I gave you at the end were the total differential formulas. So that's this is the total differential, and this is the total differential. And here you've got the total differential given with in the vector form, grad dot dx dy. So let's just give some examples of how you calculate them from particular equations or particular functions. The first part just sets up the differential commands in Maple, and here's an example. So let's see what the stages are here. All you do is it's just more practice of partial differentiation, because what you need to do is to look at the variables in that, and we've got x and we've got y. So if we have x and y, put down the dx and then just partially differentiate with respect to x. So that gives you this, partial derivative with respect to x times the dx. And then add the next variable's dy, so then go through again and differentiate with respect to y. So you find the partial derivative with respect to y, dy. That gives you your total differential. Okay. And similarly here we've got x and a w and a y. So you need to spot what variables there are. So we have three variables. I find it helps to do them in alphabetical order. I'm not sure if Maple does, it does today. Okay. So looking at the w, you go through. You're just practicing the partial differentiation again. So for the w, you have 2w squared y squared over w, which is this first part, 2w squared, 2w y squared. But because it has combined it with the other expression, it's multiplied the top and bottom by w just to simplify. And the next part comes from this, becomes 1 over w, which is this, 5x cubed and so on. So that's partial derivative with respect to w. This is with respect to x, which is much easier because there's nothing here, you just get that. And this is with respect to y again, which is easier because it's just this last part here. So it's just another really way of applying partial differentiation. Except it's a useful way of writing it out, as I'll try and show you in the next couple of bits. And here's one we have x and t and w. So you got dt, dw and dx. And just go through again and do the partial derivatives of for every variable. So for dt, you have to do this one and this one. For dw, it's only this one. And for dx, it's only this one. And finally, this looks like a Cobb-Douglas type 1 coming up. Yeah, so it's that kind of form. 0.1, 0.4, yeah, this is a Cobb-Douglas. Y to the power half. So you just go through each of the derivatives. Hopefully you're now getting good at differentiating these Cobb-Douglas ones. But here, there's also this constant here, which could be maybe technological change or something, or that kind of constant at the beginning, parameter. But you also have to put that one in, because that's why the first one looks different from the others. These are the standard Cobb-Douglas ones. Here's the parameter at the front, dt. So that has this change. That will have an impact on the final function like this. Okay, before I go on, I just thought I'd just show you what this is getting at. So here we've got t, w, and y affecting u. So t, w, x, and y are all affecting u. So what we're doing is we're going back to this situation we kind of started this series of lectures off on, which is where you have something you're interested in, could be utility, and you have some things which you think affect it, t, w, x, and something else, which we'll also look up again, t, w, x, and y. And you're saying, well, how does t, w, x, and y affect this? So what you're putting in here, by putting these partial derivatives in it, you're putting in the u, derivative with respect to t, partial derivative with respect to t, partial derivative with respect to u, to w, and partial derivative with respect to x, partial derivative with respect to y, and then instead of just, this means instead of just putting plus or minus, instead of just plus or minus here, which we had before, this gives you more information because it's also giving you the actual magnitude of change. So if you know you've got a change dt here, you multiply by this and you'll get the estimated change in u. A change in dx here, you multiply by this, you get an estimated change u. If they all four change, then you can multiply all four the changes by these derivatives and you'll get the predicted change in u. So it's making this channel diagram of effects much more powerful and more specific because you have these effects. Okay, I think we can just talk through these two examples from economics quickly. The first one is, suppose that exports depend on exchange rates and marketing technology. Marketing technology could be very important. For example, there are famously used to be factories in China making trainers for Nike and making almost identical trainers not for Nike, for their own brand, and the Nike ones would sell far more because they were well known. So marketing technology is not to be sneezed at. Of course they're caught up now. So if that's what exports depend on, imports are dependent on national income Y. The more you earn, the more you import normally, all things being equal. Distribution of income Gini. It's thought that highly unequal societies sometimes import more because the wealthier people groups start to import things like cars and so on. And again, the exchange rates. So the total trade balance is given by something like this. Then just to have a discussion about what's going to happen to the trade balance based on these factors, you can take the total differential. So you just go through and you differentiate, take the partial derivatives for each of the factors, each of the variables there are in these functions. So there's an e there, so you're going to have a dE, and so that's going to have a derivative with respect to e, and that is, so you put those in. Then you go on to dt, so this one appears, but this one does not depend on t, so that's not there. Then you go to y, so that's only this one, and you go to g, which is only this one. Then you can discuss, okay, what sign would you expect the various partial derivatives of the equation to have? So what if the exchange rate E, depending how it's measured, if you take the conventional way, as if E increases, you'd expect exports to fall because they get more expensive, and imports to rise because you have more buying power, they get cheaper and so on. So you expect this to be a positive one, this expects to be a negative one. T, marketing technology, you expect that will be positive. Y, you expect positive here because you import more, and G, you expect positive again. So this is the only one that involves 2. So because this is a positive, this is a negative, this is a positive, the balance of the size of those would depend what happens when you change the exchange rates. If you devalue, would that help or hinder? And also the relative sensitivity, which one's going to change more? And that's the famous effect whose name I've forgotten now, Marshall-Lerner effect. Okay, so what you do is you've got econometric data, you've got a whole bunch of trade data from different countries, over time for one particular country, and all these different things, and you could then estimate these different propensities and parameters. So that's the kind of thing you could be doing when you get to econometrics, macro, and trade theory. On a more micro level, we can go a bit further if you know a bit more about the variables in the model. And I think this is quite a nice demonstration of two principles, or two connected theories, concepts. So, for example, you're looking at patterns of migration from rural areas to towns, and you might think, okay, the number of migrants that arrive per week or per month, whatever you're measuring, is given by these things. So, number of migrants arriving depends on rural per capita consumption, the urban wage level, and B is just the cost of getting there. Now, there's, as always, the people that don't like quantitative analysis will say, oh, you're assuming these things, but at least I'm showing what I'm assuming. I'm ignoring other stuff, fine, but this is what I'm concentrating on today. Tomorrow I'll put some other things in. So total differential of this Comes out like that. So there's just 3 variables, so you go through each one, put in the partial derivatives, multiply by that differential change, dc, dw, dv. You get the overall change, linearly estimated change in M migration. Okay, so if we just stop for a moment and go to draw that on here. So let's just change that. So this time what we're interested in is your migration, and that's going to depend on consumption. That's not very sensible. Consumption and the wage rates. So rural consumption, the urban wage rates, and the bus fares actually get from one to the other, like so. And the change in C, but then got to multiply. I'm going to write it like this. You have to multiply it, instead of writing MC, just to be more precise, I'm just going to write it like this. The partial derivative of C, partial derivative of M with respect to C, the partial derivative of M with respect to W, and the partial derivative of M with respect to B. Okay. So if you have a change in one or more of these, you simply multiply by this and it'll predict, using that tangential method, the estimated change in M. Fine, that's what we've got so far. But let's say we've got some extra information, which we know that urban wages depend upon C, according to that famous model of Arthur Lewis that we started with. Because if C is really high, then W is going to have to be high as well, otherwise people would prefer to stay in the rural areas, and vice versa. So there's going to be a connection there. Also, the level of fares is likely to be affected by C, what people can afford and so on. Therefore, we've also got these differentials, dw and db, using these rules. So dw, if w depends on C, so w is a function of C, then the change in w would be dw by dc times dc. That's just the straightforward differential rule when you have just 2 variables. And db is equal to db by dc times dc. So that, if we put it back to the diagram, a change in W itself depends on C, and you can predict what this is going to happen here by dw by dc, and also this depends db by dc. So this is telling us something about how the variables are connected, which we don't get without that extra information. Yeah. Now, in this original total derivative, because we also know a connection between C and W, we can replace this dW by this times dC. So substitute that in. So it's this partial derivative times this partial derivative times dC. And you can replace this dB by this. So the whole thing eventually just depends on dC. So you end up with this. And at this point, you can write it in differential form. So divide both sides by c in a sense. So, and that gives you what we call the total derivative of m with respect to c, which we write like this. Now, notice what I've done here is I've written dm by dc, and this d is a straight d. It's not a curly d. So it's not the partial derivative of m dm by dc. And it's much preferable to that. So what I've found here is I've found dm by dc by combining all these effects, because this one here says what happens if rural consumption changes, how does that impact the migration, assuming that w and b stay the same. Normally you have to assume that, so we can just use the partial derivative. But of course it's completely unrealistic because we know that in fact if c changes, likely the wage is going to change and the bus fare will change if c changes. So it's not realistic to say, okay, let's assume that these stay fixed. So if we do not know what's going to happen to these, then we just have to use this partial derivative. But that's the second best. If we know what's going to happen, we have these links. We can take account of, okay, if c changes, there'll be a direct impact here, but also this will have a knock-on effect here, and then that will have a knock-on effect on migration. C will have a knock-on effect on bus fares, and that will have a knock-on effect on migration. Then we've taken all the possible, we haven't made any assumptions about things staying the same. We said, let C change, let everything else that's affected change as well, and see what the knock-on effects are, and find the effects on M. So we've taken everything into account, and we get this, which is the total derivative of M with respect to C, which isn't making any assumptions about things being fixed, so it's much more preferable. So it's vital that you remember when you've got the straight D, you're not making assumptions about things being fixed. When you've got the curly D, the partial, you are assuming that the other variables are fixed. That's the good news. The bad news is you almost always are stuck with this one because you haven't got enough information, but that's where you're aiming at to get to, the total derivative, if it is possible. Okay, and the process of finding a total derivative, if you can, is called total differentiation. Great. Okay, thanks. I think that's all for now. So now we are finally ready. We have all the ideas we need to get into the bits on optimization. So we'll move on to that in the next lecture, and thanks for watching.